So for this question we have, draw a Lewis structure for the polyatomic phosphite anion. Okay, so they want the Lewis structure for PO33 as they said there. So had they not told us that what phosphite looked like, the key thing here is that, remember not to panic obviously, but the second thing is that if we memorize our eights, our common eights that we see, so phosphate, nitrate, carbonate, it becomes easier to approach the ites, because the ites typically are just the eights but one less oxygen, still the same charge, still the same main halogen or anion there, but it's just one less oxygen. So phosphate, if you recall, is PO43 minus. So if you take away just one oxygen but keep everything the same, that's how you end up with phosphite. And yes, we can still draw a Lewis structure for it, and yes, it will still make sense. It will just be a little bit more haphazard than the phosphate ion. Okay, so with that being said, phosphorus, 15th column, that is going to be 5 electrons. Oxygen, column right over, 6 electrons, and there's 3 of them, so that's 6 times 3, so that's 18 that it contributes, 5 that it contributes. And when I say this, I'm referring to their valence electrons. And then we have the 3 minus, so it would be plus 3. So that'd be 5 plus 18 plus 3. And we have 26. Okay? So now, because phosphorus has the most unpaired electrons, we're going to put that one in the middle. Okay? And so we have 1, 2, 3 for the 3 oxygens. Okay? And now we're going to fill out the valence electrons as much as we can. Oxygen right now is sharing one of its 6, so 2, 3, 4, 5, 6. Same thing, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6. Okay, and phosphorus right now is sharing 3 of its 5, so it's going to be 4, 5. Now, what we cannot forget though are the extra electrons that are added to even stabilize this. So with this being said, actually, funny enough, we're going to have 1, 2, 3. Okay, we're not done quite yet because there's still a bit of work to do, but let's just check now to see if we have the right amount of electrons. So there's 3 bonds, so that's 6 electrons right now, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lone pairs. So that's 20 electrons plus the 6 from the bonds. We do indeed have 26 electrons. Now let's check out the formal charges to see if this is a stable, or at least the most stable thing they would prefer. So with phosphite, phosphorus likes to be 1 lone pair and 3 bonds. That represents a formal charge of 0. Okay, that is its most stable form, because that is when the unpaired electrons become bonds. Oxygen, on the other hand, it only has 2 unpaired electrons, so when they become bonds, this will represent its formal charge of 0. But as you can see here, for every oxygen, what happened was that the formal charge is changed because one bond is replaced by a lone pair. When that happens, we become more negative. So each oxygen is actually going to be -1, which coincidentally is perfect because that's how we end up with the PO33-. Each oxygen has a formal charge of -1, which is how this molecule in general has that anionic charge of -3. So theoretically, this would be our Lewis structure for the phosphite anion. The phosphorus really, I could rearrange it, but the phosphorus has no need in this case to take on the negative, because oxygen is a more electronegative atom. So it would, if any of them, they would be the ones to prefer to carry the burden of having more electrons, as long as the octet rules are satisfied, which in this case they are. So with that being said, that's what they get. So still single bonds, perfect. And yes, everything is just added right there. And this will be the best shape for it. As you can see, each oxygen is where the -1 charge is, and that is how we get the phosphite ion. All right. Let's move on to question number 3. Okay.